Hello everyone. Today I'll be talking about our work on online system identification in changing environments. The model of a system changes as the environment changes. Traditionally, system identification has been treated as a reactive problem. Observed errors are used as feedback to update the model. However, in this work, we wish to explicitly model the effect of the environment. The application we're looking at is the ability to predict wheel slip of a robot as it moves across different terrains. This information is useful for various modules such as motion planning that can use a slip map as shown in the figure to decide which route to take. What distinguishes this from a plain regression problem is that the training data distribution and the test data distribution do not match. The training data distribution is diverse and collected from various trials, while the data distribution is focused on one particular trial and is changing as the robot is moving across different environments. The formal problem statement is as follows. We assume the dynamics of the system depends on slip parameters. We're given as training data a pair of features and slip parameters. The features are visual features extracted from the image at a particular time step from the lower third of the image. This corresponds to the terrain that the robot is about to move over, and the slip is measured from that part of the terrain. The objective then is as follows. We wish to maximize the likelihood of the model which describes the relationship from features to slip over a particular data distribution. The question is, what is this distribution? The desire is to find the most likely model on the target distribution. However, in our case, the target and the source distribution do not match. This general class of problem is called domain adaptation. The approach we adopt is called instance weighting, where every element in the training database is given an importance value, which corresponds to the density ratio estimate between the target and the source at that data point. To illustrate the point, a simple 2D example is shown where logistic regression is used to weigh the training distribution. The portion where the source and target distribution overlap is given high weights, while the portion where the source distribution is far away from the target distribution is given low weight. In our work, not only is the target distribution unknown in advance, but it also changes as the robot moves across different terrain. In the video shown on the left is the image data stream from a trial, and on the right is a low dimensional projection of the high dimensional visual features for visualization purposes. There are three kinds of terrain: asphalt, gravel, and grass, shown in red, green, and blue respectively. The current estimate of the target distribution is shown in black. As a robot moves across different terrain, this target distribution changes. The following diagram shows an overview of our approach. The training database is a diverse collection of images collected over various trials along with corresponding slip values. The test data stream is the features observed by the robot during one particular trial. This is then given to an estimation window which retains a finite history of features. The domain adaptation then uses this information to reweight the training database and provides these weights to a weighted linear regression model, which updates the model of the system. We use a dataset collected with a husky robot equipped with a camera as it moves over three different kinds of terrain: asphalt, gravel, and grass. For features, we use a 512-dimension text-on dictionary. The following video shows how domain adaptation works in practice. The main window is the target data stream, and on the right-hand side are the top 5 training sample images according to the weights assigned by domain adaptation. As the robot moves to grass, most of these images correspond to images of grass. As the robot transitions to asphalt, the system identifies that the target distribution has changed and more pictures of asphalt appear on the right-hand side pane. We see that on average, domain adaptation improves over unweighted linear regression on 4 out of the 5 trials because of the ability to focus on part of the training data set that really matters. It's interesting to note that in one of the trials it does worse than unweighted linear regression, and this is because an error in the estimation of the density ratio can actually throw off the linear regression and make it perform worse than the unweighted case. Another problem we encounter is that the speed of the robot affects the target distribution rate of change, which is unknown in advance. For example, having a window size that is too large or too small can result in an incorrect estimation of the target distribution, which can affect the performance of the domain adaptation algorithm. To overcome this shortcoming, we consider a second variant of the problem statement, where the robot can measure the slip as it moves over the terrain. This measured slip can then be used as feedback to determine the best window to be used for a particular trial. We frame this problem as a no-regret online learning problem where our experts are windows of different size. We use randomized weighted majority algorithm to select the best expert in hindsight. The loss function in this case is a squared difference between the actual measured slip and the estimated slip. To test this algorithm, we evaluate it on a dataset which are played at different speeds to mimic the robot moving at different velocities in the environment. When the robot is moving at slow speed, a large window is the optimal window size because it allows for a better estimate of the target distribution. When the robot is moving at a very fast speed, a very small window size is preferred given how fast the target distribution is changing. We compare the mixture of window experts with online linear regression, which updates the model with the accumulated test and training data. Window of experts still outperforms online linear regression because of the fact that while online linear regression uses all of the data to fit the hyperplane, the mixture of window experts focuses this on a particular part of the training database. In conclusion, we first showed that training and target distributions for online system identification are in fact different. Domain adaptation tries to address this problem. We use a particular type of domain adaptation, which is reweighing the training dataset, and use a sliding window to estimate this changing target distribution. Finally, we also use a mixture of window experts to find the best window size for a particular trial. Thank you.